the electromagnetic spectrum, from nanometers to microns, and now I'll be talking about observations in the centimeter range with MINER XBand bistatic observations. Which of the buttons advances the slides? Do spacebar arrows? Nope, not working. Oh, there we go. Okay, so let me first introduce you to the XBand bistatic architecture. Some of you may know, some of you may not. But we operate as a bistatic instrument. So our receiver and transmitter are not co-located in the same place. In this case, MINER-F is the receiving system, the receiving antenna, and we transmit a signal and bounce it off the moon. We transmit that signal from the ground with an antenna, 34-meter dish, DSS-13, which is part of the Goldstone solar system radar complex. Now, we transmit the same signal we would as if MINER-F had been the transmitting antenna. So we're collecting the same data we did when LRO first launched and MINER-F was a monostatic system, and allows us to collect a variety of products to give us information about the physical properties at radar wavelengths of lunar materials down to the penetration depth of the system. And so, you know, if you take anything from all the text in this slide, look to your the bottom left in the slide. Oh, can you go back? Okay. And I want you to take note that we have a spatial resolution of about 100 meters. So it's 100 meters per pixel. It varies a little bit, but based on the geometry with which the data was collected, but it's around 100 meters. We have a sensitivity to the radar properties of scatterers and absorbers in a penetration depth, the wavelength scale penetration depth. We have a sensitivity about 4.2 centimeters. So in the centimeters range, down to about half a meter, we're sensing the distribution of scatterers and absorbers in the lunar surface. Now, we use these data to gain insights into a variety of processes on the moon, volatile impact and volcanic processes. I'm going to concentrate in the interest of time on just volcanic processes. Parvati Prem gave a talk in this session, I think the previous talk in the session next door on some aspects of volatile research we're doing. Angela Stickle has a poster today looking at impact processes. Gareth Morgan will be talking in the next session about volcanic processes. I chose volcanic because I had to choose one. Sorry, Gareth, I'll steal a little bit of your thunder. But hopefully I'll set you up well so you don't have to re-explain MINER-F an hour from now. So one of the things I want to point out, you know, radar data, collecting and processing radar data is not an easy endeavor in and of itself. But when you are in a bistatic architecture, there are some additional complications that are incurred. There are multiple signals we're trying to both collect and avoid. And MINER-F wasn't built with collecting data in a bistatic architecture in mind. And so we had to develop the methodology for forming images and collecting these data while we were in flight. And so we've learned a lot. We first started collecting XBand data in 2017. We had been collecting SBand data, the other frequency MINER-F operates at, for a number of years previous. And as these things typically go, you start to collect your XBand data, you expect it to be just like the SBand, right? We learned a lot. We collected our first data. It didn't look quite right. It didn't look how we expected it to look. We had a number of processes in place that we thought were gonna give us good quality data. And so we had to start looking at those processes and trying to break down where we had some discrepancies that would allow us to create the kinds of quality images we were getting at SBand previously. And we have gotten to that point. Now we've had to make a number of changes. We've done a lot of work, but what I'm showing you in these two images are the same part of the surface or the same radar image. We've reformed the data on a slightly different part of the surface where we know the data quality is very good. So we've learned a lot, and we want to start taking that data and applying to the surface and learning things about the moon at XBand. Now, I mentioned that we are also an SBand instrument, and we have good quality data at SBand. And really, there's a lot of power in looking at radar data at multiple frequencies. Because as I mentioned, we're sensitive at XBand to centimeter scatterers. SBand wavelength, we're sensitive to tens of centimeter scatterers. And we do have ground-based data of the moon at P-band, which is sensitive to 70 centimeter and higher meter. You could think of it as almost meter scale scatterers. So we can look at the surface and try to understand what it's telling us about the composition and physical properties like roughness at a variety of wavelengths to really kind of get at some interesting questions around the moon. And so I said I was going to talk a little bit about volcanic processes. I wanted to show this slide real quick. A portion of Mare Imbrium turned on its side. The top image is a WAC portion of the WAC global mosaic, where you can see the stark differences between the highlands and the Mare, and some variations within the Mare. But when you look at the radar data overlaying on there, and in the middle is SBand radar data, you see a lot of fine detail that's related to surface roughness, may also be related in some ways to composition, and may also be giving us a sense of stratigraphy within the Mare, because again, we have some penetration depth. So we're not just seeing the surface, we're seeing into the subsurface. And Gareth Morgan has shown in a number of meetings this inset that I have at the bottom right in your screen, where we're seeing indications of flows within Mare Imbrium in the SBand data. And it's a little brighter in power where we're seeing, and I've got it defined by these orange arrows. That could mean it's a little rougher or a slightly different composition. We also can collect XBand data of the same area. And so in this bottom image, we have an XBand, XBand data collected over there, and we can take a look at the same inset. And we don't really see those clear indications of a flow in the same area. And that can be telling us, again, a little bit about specific roughness of that flow, or it could be telling us about the depth of that flow, how far it is buried in the subsurface. We can also look at pyroclastic deposits. The Aristarchus Plateau has been well studied by many instruments, but we do have really good ground-based data of Aristarchus at P-band, and we've collected a fair amount of S-band data. Unfortunately, Arecibo Observatory is no longer active, and so we can't collect S-band data in a bistatic architecture currently, but we did get about 2/3 of the Aristarchus Plateau at S-band over the course of Miniraf's bistatic campaign. And we can see a lot of clear features demarcated, I should have found a better word than that, in the radar data, right? You can clearly see the boundary of the pyroclastic deposit with surrounding terrain, but we also can see a few other things. So the blue arrows were that boundary with the pyroclastic deposits. Those orange arrows that you hopefully can see in the image are pointing out some secondary impacts from the Aristarchus impact, where we can very, very distinctly observe the roughness characteristics of those deposits as they radiate from the primary crater. And we can look also at XBand. We have a couple of strips. We actually have a couple more strips that we've collected recently. I didn't include in this particular image, but we can start looking at various wavelengths, trying to get a sense, one, about if there are thickness variations in the pyroclastic deposit, and Gareth may talk a little bit more about that later today, and also what are the characteristics of those secondary craters and the material that they deposit on the surface, and do they have specific size scales or distributions of scatterers. We can also look at some other interesting areas, or we are looking at some other interesting areas. One of those is the Atlas Thermophysical region. So this has been discussed with Diviner in a number of forums, and this kind of white outline you see on this map of a portion of that region indicates where the boundary of this thermophysical region is in H parameter maps of the moon. But the underlying image is actually P-band radar. And it's an interesting correlation that we see between P-band radar and the Diviner data. It's not clear what the meaning of that potential correlation is. We tend to think of the kind of signatures we're seeing in this image at P-band to be representative of dark halo deposits surrounding impact craters. But, you know, the Diviner H parameter shouldn't be picking up dark halos, right? what we tend to see with divine air HMAP in these kind of thermophysical regions or these cold spots are indications of freshness of the deposit. But this is not very young. So there is still, there is something really interesting here. We've been collecting SBand data of this region, and we've started collecting more XBand data. And so again, we want to try to take a look across a number of wavelengths to try to see if we're observing at P-band as something at depth, something near the surface, see if we can make a connection with those, with that H parameter map. And was that a 3-minute, Deborah? I didn't. Well, here's the summary. Okay, we're acquiring XBand bistatic radar to a variety of terrains, looking at pyroclastic and volcanic deposits, really interested in the Atlas thermophysical region, and just wanted to put off to the side here, you know, I was showing comparisons between S and XBand data. We're starting to collect enough XBand data that we can make comparisons just with that. And I'm showing, again, a portion of Mare Imbrium where we have 5 collects that we've made over a similar, and we're seeing some variations in roughness. So if you look up in these collects on the right, this is circular polarization ratio, so a measure of roughness. We see in the blue less roughness, but we're still in the Mare deposit, and we're getting to much rougher deposits before we get to the highlands where it gets a little smoother again. Really interesting. We're starting to look into this, and hopefully you'll be seeing some results coming from that soon. Thank you.
Thank you, Wes.